All right, so today I'm going to introduce to you guys a couple different ways that we can apply logarithms in real life. So a couple of those things are when working with pHs, when working with the Richter scale for earthquakes, and then decibel levels for sound as well. So our first one that I want to look at is the pH scale. As many of you guys know, if you've taken chemistry or if you're currently taking chemistry, the pH scale is how we measure acidity or alkalinity of a chemical solution. So this is a formula that we use to measure this. And we know the acidity or alkalinity of a solution is based on the concentration of hydronium ions in that solution. So for those of you, if you haven't taken chemistry, basically like the hydronium ion concentration is what's going to determine how acidic or basic a function is. So over here, I have like a little scale for you guys for common things that have certain pHs. So things that are neutral would be like pH of 7, which would be something like pure water. Milk is pretty close to that. Blood is also pretty close to that. And then as we go down the scale, we get more acidic. As we go up the scale, we get toward the bases, so more alkaline. So things like bleach are very basic, where on the other end of things we have like things like vinegar, lemon juice, stuff like that, so more acidic. Okay, so a toilet bowl cleaner has a hydronium ion concentration of approximately 0.1 moles per liter. What is its pH? Okay, so we're going to plug in that hydronium ion concentration into this formula here. I don't know. Do you guys learn this formula in chemistry?
We did. I just forgot about it.
Yeah? Okay, so literally all you have to do for this one is you're just going to plug this into your calculator, so negative log of 0.1, and we should get the pH of the solution.
1.
Get a pH of 1? Okay, the pH is 1. Okay, when I say something has a pH of 1, this is what I'm really saying. I'm telling what the hydronium ion concentration is of that solution. So when you say something has a pH of 1, you're saying the hydronium ion concentration is equal to 10 to the negative 1. Okay, and that's literally what 0.1 is equal to. Okay, so that's why the pH scale works with the common logarithm, because it's all bases of 10 when we talk about hydronium ion concentration. Okay, so and this is part of the reason why logs with bases of 10 are called the common logarithm, because we have a lot of systems that are base 10 systems. Okay, so the pH of this solution is 1. Okay, egg white has a hydronium ion concentration of approximately 1.585 times 10 to the negative 8 moles per liter. Is egg white acidic or alkaline? So again, we're just going to plug into our formula here. When I say times 10 to the negative 8, we're saying take that decimal and move it left 8 times. But you should be able to just enter that directly into your calculator inside the logarithm. Pierce.
Sorry, this just came in my mind really quickly. I thought we weren't able to take the negatives of the log.
So if the negative is inside the log, yes, but I can multiply any logarithm by a negative. That's okay. Yeah. Alexandra? 7.799. Okay, so can we say approximately 7.8? So this is pretty close to neutral, but would we say this is more acidic or more alkaline?
Alkaline.
Okay.
Okay, so alkaline is another word for basic.
Yeah.
Where would alcohol be on this chart? Basic or is it?
Good question. I don't know. Google knows. It's probably different for different
That's small
things.
alkaline.
Most of what we drink is
Well,
around
this is
7.
beer, though.
Beer is 4. There you go. More on the acidic side, yep. Okay, the other version of this question is it gives you the pH. It gives you the pH and you solve for the hydronium ion concentration. So in the formula, I would be plugging in 2.2 for pH. And then our job is to isolate for hydronium ion concentration here. So before I do anything, I need to actually divide out this negative. Okay, I can't use inverse form until I've done that. Okay, if I want to isolate for something inside a logarithm, I need to think about what the base of that logarithm is. And again, we need to use inverse form for this. So can someone express this in exponential form for me?
10 to the power of negative 2.2.
Okay, so I'm switching from logarithmic form into exponential form here. Can someone calculate this for us?
6.309573445.
Times 10 to the power of negative 0.
Yeah.
10 to the power of 0.3?
No, 10 to the power of negative 3.
Oh. So sorry, Jonathan, what was it, 6.509, did you say?
6.3 times 10 to the negative 3.
Okay.
That's what I got.
So do we just ignore the times 10?
No. Because this means take the decimal and move it left 3 times, so you can't ignore that. And units of measurement for hydronium ion concentration? Moles per liter. Great. Okay, so either you're given hydronium ion concentration, you plug it in and calculate, or you're given pH and you find hydronium ion concentration. Okay, the next one is for looking at different sound levels. So you can see a little chart that I made for you guys over here for the different sound levels. So something like the rustle of leaves or a whisper is between 10 and 30 decibels. Whereas a shout can go up to 60 decibels. That's normal conversation. A shout can go up to 80 decibels. Something that is at the top of the scale would be like a rocket, which in that case would be a sound if you're right near it, and listening to that without any protection is potentially fatal. A jet engine would be like the pain threshold, basically. Yeah, so we can use this decibel formula, or the sound formula, I guess I should say, in order to compare the intensities of sounds. So when you see beta 2 minus beta 1, we're talking about the difference in sound levels, so the decibel difference. And then when we see I2 and I1, this is talking about the ratio of the intensities of their sound, and the way that this is measured is in watts per square meter. Okay, so what I plug in for beta 2 should match the intensity of, those two subscripts relate to the same sound. So it should match intensity 2, and then beta 1 matches intensity 1. Most of the time, it will give you the full ratio of the intensities in and of itself. Okay, so a couple examples of this. How many times as intense as the rustle of leaves is the sound of a shout? So if you guys look at your chart here, the rustle of leaves is 10 decibels. You can see it right there.
Will you ever give us something that's not on the chart, so the sound of
If I do, then I have to give it to you
Okay.
in the question. I'll have to give you the decibel level. Yep.
Are these charts going to be on the test?
Yeah, so if I want you to use the chart, then I'll put it on the test, or I'll just give you the decibel levels in the question. Okay, decibels.
These equations will be on the test.
Pardon?
Are these equations?
The equations will be on the test, yep. Okay, you just need to know how to use them. Okay, so normally if I'm comparing a louder sound to a quieter sound and it's saying like how many times more intense, I'll do the louder sound minus the quieter sound.
Sorry, isn't that show 60?
No, the values are above the labels here. So shout is 80. Normal conversation is 60. So I'm going to do the louder sound in beta 2. So the sound of the shout minus the sound of the rustle of leaves. And then if I'm looking for how many times more intense something is than another sound, I'm really actually isolating for the full ratios of the intensities here. So I'm actually isolating for the entire variable of I1 over I2. I2 over I1, yeah, thank you. So this is 70. I'm also going to divide out that 10 there.
Why can't you just do 80 minus 10? Why do you have to do all the one stuff?
What? Because I'm isolating for I2 over I1. Okay, so we get 7 equals the log of intensity 2 over intensity 1. And how do we solve for I2 over I1 here? How do I get that out of the logarithm? What's that, Jeremy? No, we can't divide out of a logarithm like that.
It'll give you like 10 to the power of 7 equals I2 over I1.
Yep, so we're going to use exponential form here. Switch the form. The base of the logarithm is 10, just to remind you, that's the common logarithm. And that's actually what I'm trying to isolate for here. So I2 over I1. So what we would be saying here is this is 10 million. So therefore, the sound of a shout is 10 million times as intense as the rustle of leaves.
So you don't have to like isolate I.
Nope. We're comparing the intensities of those sounds. Okay. Okay. The other thing that you might be given is like 1 decibel sound level and then the ratio of the intensities. So in part B here, we're given the sound level of Niagara Falls, which is 90 decibels. And then the sound level of an emergency vehicle siren is about 316 times as intense as the sound level of Niagara Falls. What is the sound level of an emergency vehicle siren in decibels? Okay, so I'm given that I2 over I1, the ratio of the intensities is 316. So if I did I2 divided by I1 and I got 316, did I divide a larger number by a smaller number or a smaller number by a larger number? We need to kind of use our common sense here.
Larger by a small number.
Okay, so in order to get 316, I must have done a large number or a larger number divided by a smaller number, right, to get a value of 316. If I do a small number divided by a larger number, like 7 divided by 100, I get a decimal. If I do something larger, like 20 divided by 4, I get a value that is above 1, right? Greater than 1. So if I've gotten a value that is greater than 1, then I must have done a larger intensity divided by a smaller intensity. So which one is the louder one here, Niagara Falls or the emergency vehicle? Okay, so beta 2 is the decibel level of the emergency vehicle. That's our question mark. It's the louder.
What does beta mean?
It's just like a symbol, like theta or x or anything like that. Okay, and then I'm going to set beta 1 at 90 decibels because that's the quieter sound. Okay, and I know that because I said I2 was the larger intensity or the greater intensity. So greater intensity means larger sound or louder sound, right? Okay, let's plug this into our formula. We have beta 2 minus beta 1 equals 10 log of I2 over I1, which we know is 316. Okay, with these ones, you need to kind of use your common sense. It's easy to calculate after we've put it in, but you need to choose the correct beta 1 and beta 2 based on what your ratio of your intensities is. Okay, so I'm just going to really calculate this by calculating 10 times the log of 316. And then once I've calculated the log of 316 times 10, I'll add 90 to that answer. Make sure the plus 90 does not get included inside your logarithm. We're just adding that after we do that first part.
Wait, why does 360 equal I2 over I1?
Because it says that the siren is 316 times as intense. So it's telling us the ratio of how intense one thing is compared to the other thing.
I got 315.0. Sorry, 115.0. I don't know why I got set 3.
I got 114.
You got 114?
Yeah, 114.99.
Okay, so approximately 115 decibels. That's good. And then we will do a quick therefore sentence. Therefore, the emergency vehicle siren is 115 decibels. Okay, so use your discretion. If I tell you that something is 1/300th as intense, then I'm obviously saying 1 is I2 and 300 is I1. So the louder thing actually goes into I1 and the quieter thing goes into I2. So just be mindful about what that ratio of intensities is telling you. Okay, you can also use your common sense by the time you get to this final answer. If we've decided that the emergency vehicle siren is louder than Niagara Falls, of course I should get a higher decibel level. So you can kind of do like a bit of a guess and check thing here if you've entered it in incorrectly into the spaces. If I get something that's less than 90 and I say that the emergency vehicle is louder, that doesn't make sense, right? So use your common sense once you get to the final answer here. So I'm saying like if you had 1/300, let's say, as your value of the ratio of intensities, then I2 is the quieter thing and I1 is the louder thing. Okay, last application here is the Richter scale. There are other applications as well, but these are the three main ones that we're going to look at. So M is going to be the magnitude of an earthquake measured using the Richter scale. I over I initial or I naught is the intensity of the earthquake being measured. So I is the intensity of the earthquake and I naught is the intensity of like a standard low-level earthquake, which those types of things are happening at all times. We just don't, they're so low that we don't feel them. So oftentimes, like, we don't have to enter anything into this. It's just saying that these intensities of these like magnitudes of these earthquakes are measured off of like a really like standard low-level earthquake that no one can feel, but we can still detect it. Okay, so how many times, also with this one, if we wanted to compare two earthquakes, I could do something similar like I did with the sound, and I could do M1 minus M2 if I'm comparing the magnitudes of two earthquakes, and then it would be like I2 over I1. So this is used to compare two earthquakes. So add that as well. You can add it there or add it below. Okay, so example 3A says how many times as intense as a standard earthquake. is the earthquake measuring 4.1 on the Richter scale. So this formula measures against that standard low-level earthquake. So again, I'm looking for the ratio of the intensities of those earthquakes. So if I plug in my magnitude here, I'm really just looking for how that intensity compares to the intensity of that standard low-level earthquake. So how do I solve for I over I initial? How do I get that out of the logarithm? Pierce? Yeah, exponential form. So the base currently is 10.
So 10 to the power of 4.1.
Yep. And that will give me I over I naught.
So 12,589.
Okay?
0.2.
0.2, perfect. So therefore, an earthquake measuring 4.1 on the Richter scale is 12,589.2 times more intense than a standard low-level earthquake. Okay, what is the magnitude of an earthquake 100 times as intense as the standard level earthquake? So in this case, we're solving for magnitude, and we're given the ratio of the intensities of those earthquakes. Okay, so this is really just a quick, straight calculation. Two. Okay, so an earthquake 100 times more intense than a standard earthquake would measure 2 on the Richter scale. Okay, that one's just literally 10 to what exponent equals 100. You shouldn't even need to really use your calculator on there. Okay, as you go up with magnitudes, so magnitude 2 versus magnitude 3 versus 4, each level is 10 times more intense than the previous level of earthquakes. So something with magnitude 3 is 1,000 times more intense than your standard low-level earthquake. Okay, if I were comparing two earthquakes, let's say I wanted to compare something that was 4.9 and 3.7, then I would use this and I would isolate similarly and I'd be finding I2 over I1. Okay, so you'll see some of those in your applications stuff as well.